നമുക്കിന്ന് Zenerdiode it is already been discussed that when the reverse bias on a crystal diode is increased, what happens? A critical voltage called a breakdown voltage is reached, where the reverse current increases sharply to a high value. അപ്പോൾ നമ്മൾ ഈ പിക്ചർ നോക്കാം നമുക്ക്. ഓക്കെ, ഇത് forward characteristics, the reverse characteristics. So if you increase the reverse bias of a diode, what happens? A sharp increase of the current. The y-axis is the current. This is the reverse current, this is forward current, this is forward voltage, this is reverse voltage. A sharp increase in the current happens. The satisfactory explanation of this breakdown of the junction was first given by the American scientist Zener. Therefore, the breakdown voltage is sometimes called Zener voltage, and the sudden increase in current is known as Zener current. അപ്പോൾ ഈ വോൾട്ടേജിന് ഈ പർട്ടിക്കുലർ ഷാർപ്പ് ഇൻക്രീസ് ഉണ്ടാവുന്ന ഈ പോയിന്റിനെ നമ്മൾ ഈ വോൾട്ടേജ് എന്നും ഈ കറണ്ടിന് കോൺസ്റ്റന്റ് ഷാർപ്പ് ഇൻക്രീസ് ഇൻ കറണ്ട്, ദിസ് കറണ്ടിന് Zener current എന്നും പറയും. The breakdown or Zener voltage depends upon the amount of doping. അപ്പോൾ ഡോപ്പിങ്ങിനനുസരിച്ച് ഈ വോൾട്ടേജ് Zener വോൾട്ടേജ് ചിലപ്പോൾ ഇങ്ങോട്ടേക്ക് മൂവ് ചെയ്യാനോ അല്ലെങ്കിൽ ഇങ്ങോട്ടേക്ക് മൂവ് ചെയ്യാനോ സാധ്യതയുണ്ട്. It depends on the doping. If the diode is heavily doped, depletion layer will be thin, and consequently the breakdown of the junction will occur at a lower reverse voltage. On the other hand, a lightly doped diode has a higher breakdown voltage. When an ordinary crystal diode is properly doped so that it has a sharp breakdown voltage, it is called a Zener diode. അപ്പോൾ നമുക്കൊരു ഡെഫിനിഷൻ അങ്ങനെ പറയാൻ പറ്റും. എ പ്രോപ്പർലി ഡോപ്ഡ് ക്രിസ്റ്റൽ ഡയോഡ് വിച്ച് ഹാസ് എ ഷാർപ്പ് ബ്രേക്ക് ഡൗൺ വോൾട്ടേജ് ഈസ് നോൺ ആസ് എ Zener ഡയോഡ്. Zener ഡയോഡിന്റെ സിമ്പിൾ നമുക്കറിയാം. Zener ഡയോഡിന്റെ സിമ്പിൾ ഇവിടെ കൊടുത്തിട്ടുണ്ട്. ഇസഡ് വെച്ചിട്ട് ഇവിടെ Zener ഡയോഡ്. The following points may be noted about the Zener diode. A Zener diode is like an ordinary diode except that it is properly doped so as to have a sharp breakdown voltage. A Zener diode is always reverse connected, that it is always reverse biased. A Zener diode has sharp breakdown voltage called Zener voltage Vz. When a forward bias, its characteristics are just those of ordinary diode. The Zener diode is not immediately burned just because it has entered the breakdown region, as long as the external circuit connected to the diode limits the diode current to less than burnout value. The diode will not burn out. നമുക്ക് ഒരു വീഡിയോ നമുക്ക് കണ്ടു നോക്കാം, കുറച്ച് കൂടുതലായിട്ട് നിങ്ങൾക്ക് അറിയാൻ പറ്റും.
In this video, I'm going to talk about Zener diodes and how you can use them to protect your circuits from sudden voltage spikes, and how you can use them as a cheap voltage regulator. You can even use them as part of an audio distortion circuit. Let's get started. The first thing to know is that the circuit symbol for Zener diodes looks very similar to the other diode symbols. Make sure you don't get them confused because they behave very differently and they're used for very different things. So what's special about Zener diodes? Well, with a regular diode, current can only flow in one direction. But Zener diodes can actually allow current to flow in both directions. This may sound confusing at first because the whole point of a diode is to only allow forward current, but I promise you they are useful. Think of Zeners like this. They're kind of like two diodes in parallel, facing in opposite directions, each with different voltage drops. When you try push current in this direction through the Zener diode, there's a forward voltage drop that's typically around 1 volt. The diode won't even turn on and allow current to flow unless you have at least 1 volt. And when the Zener is on in the forward direction, we say it's forward biased. But going the other way, there's a different voltage drop, called the Zener voltage, or VZ. In this example, it's 3.3 volts. This Zener diode will not allow current to flow in this direction unless there's at least 3.3 volts across it. But once there is sufficient voltage, the current can flow in this direction, and you'll get a constant voltage drop of 3.3 volts. Since current is flowing backwards, we say that the Zener diode is reverse biased. This property of having a predictable voltage drop is what makes Zener diodes useful. If you set your circuit up just right, you can use Zener diodes to limit the voltage that other devices receive. Let's say you have a circuit that has a voltage input, and you're worried that you might destroy it with too high a voltage. It could be a microcontroller or an op-amp that can only handle 3.3 volts on the input, and sometimes the voltage reaches 10 volts, or even minus 10 volts. You can use the classic Zener voltage clamping circuit to solve this problem. It's just a resistor and a Zener diode in this arrangement. This circuit will clamp the voltage to a maximum of 3.3 volts and a minimum of minus 1 volt. Let's see how it works in real life. I'm using my wave generator here to generate a triangle waveform that goes from minus 10 volts to plus 10 volts. For this example, the frequency doesn't matter. On the breadboard, I have a 1K resistor and a 1N5226 3.3 volt Zener diode. I'm feeding in the minus 10 volt to plus 10 volt wave, and I'm measuring the clamped output on my oscilloscope. Over here, when the input voltage is minus 10 volts, there's enough voltage to forward bias the Zener diode. Some current flows through the Zener diode and some flows from the output. The forward voltage drop is 1 volt, so it effectively clamps the output voltage to minus 1 volt. Now, between minus 1 volt and 3.3 volts, things get interesting. There's not enough voltage to turn on the Zener diode in either direction, so it's like the Zener diode doesn't even exist in the circuit. Current flows straight from the input through the 1K resistor to the output. Because of this, the input voltage and the output voltage are exactly the same. Now when the input is above 3.3 volts, we have enough voltage to fully reverse bias the Zener diode. Current flows through the Zener in this direction, and some current also flows to the output. Since the Zener voltage drop is 3.3 volts, the output voltage gets limited to 3.3 volts, and our voltage-sensitive circuit is saved. For the musicians out there, here's another example with an input sine wave that's between plus and minus half a volt. The Zener diode allows the signal to pass through relatively unchanged. Now watch what happens when we increase the amplitude of the input signal to 10 volts peak to peak. The output gets distorted. The top and bottom of the sine wave get clipped off, and our output is swinging from minus 0.8 volts to plus 2.6 volts. Notice how that's different to the minus 1 volt to 3.3 volts I was showing you in the previous example. That's because the exact voltage drop across a Zener diode will depend on the amount of current flowing through it, just the same as any other diode. Anyways, there are lots of different ways to use this technique, and if you search for diode distortion circuits, you can find some examples. So that was
അപ്പോൾ നമുക്ക് മറ്റൊരു വീഡിയോ കൂടി നമുക്ക് കണ്ടു നോക്കാം. Zener ഡയോഡിന്റെ കുറച്ചുകൂടി നമ്മൾ അടുത്ത ടോപ്പിക്കിലൊക്കെ ഡിസ്കസ് ചെയ്യാൻ പോകുന്ന കാര്യങ്ങൾ നമുക്ക് നോക്കാം.
Today we are celebrating our 500th episode with our Build Inside the...
In this lesson, we're going to talk about Zener diodes. But to begin, let's compare the Zener diode to a conventional diode. On the right, this is the symbol for a Zener diode. Now, a conventional diode is designed to allow conventional current to flow in the forward direction. So this would be the positive terminal, and this would be the negative terminal. In a Zener diode, current can flow in the forward direction like a conventional diode, or it can flow in the opposite direction. Now, a Zener diode is designed to operate in the reverse bias mode. In this mode, the Zener diode has a certain reverse breakdown voltage, and it's basically the rating of the Zener diode. So let's say if we have a 12 volt Zener diode. So when you place it in reverse mode, if the voltage is 12 or more, it will conduct in that direction. So let's give some examples. Let's apply it to a typical circuit problem. So let's say we have a battery and we have a current limiting resistor in series with a Zener diode that's in reverse mode. Now let's say the rating of this Zener diode is 12 volts. And let's say we have a 1 kilo ohm resistor. Now what's going to happen if the battery is a 5 volt battery? What is the current in this circuit? Is the circuit on or is it off? Now, because the input voltage of the circuit is less than the reverse breakdown voltage of the Zener diode, no current will flow in this circuit. So the circuit is off. The current that's flowing in this resistor is 0 amps. Now let's say if we connect a voltmeter across the Zener diode, what voltage will it read? Now because there's no current flowing in the circuit, the voltage across the resistor is 0 volts. So therefore the voltage across the Zener diode that will be picked up by a voltmeter will be the same as the voltage of the battery. It will be 5 volts. Because these two, they have to add up to 5. So now let's use the same circuit, but this time we're going to increase the voltage of the battery. So let's make it, in this case, 14 volts instead of 12 or 5. Now, is the circuit on or is it off? Because the input voltage exceeds the reverse breakdown voltage of the Zener diode, the circuit is going to be on. And so there's going to be a current flowing through this resistor. So how can we calculate the current in this circuit? How can we find the answer? In order to find the answer, it's important to understand that the Zener diode serves as a voltage regulator. So as long as the current is around basically the characteristic current for this particular Zener diode, let's say if it's small, it's not too large, the voltage across the Zener diode will remain approximately 12. It might vary a little, but for the most part, for all practical purposes, we're going to say that it's about 12. It could be 11.9, 12.1, but it's going to be fairly constant. So that means that the voltage across the resistor has to be 2 volts, because these two, they have to add up to the voltage of the battery. So we have 2 volts across a 1 kilo ohm resistor. So if we use V equals IR, then the voltage, well, the current flowing through that resistor is going to be the voltage divided by the resistance. So it's going to be 2 volts divided by 1,000 ohms, which is going to be 0.002 amps or 2 milliamps. So that's the current that's flowing in this circuit. But it's important to understand that the Zener diode will maintain a relatively constant voltage of 12 volts when it's in reverse bias mode, and if the input voltage exceeds that value. That is the rating of the Zener diode. Now let's increase the voltage of the battery.
In order
ഓക്കെ, നമുക്കിനി അടുത്ത ക്ലാസ്സിൽ ജനർ ഡയോഡിൻ്റെ ഈക്വലന്റ് സർക്യൂട്ട് നമുക്ക് ഡിസ്കസ് ചെയ്യാം. അത് കഴിഞ്ഞാൽ ഹൗ ഡു വി യൂസ് ഇറ്റ് ഫോർ സ്റ്റെബിലൈസിങ് ദ സർക്യൂട്ട് നമുക്ക് നോക്കാം. ഓക്കെ, താങ്ക് യു.